Well, welcome to our network seminar. So today we have our speaker is Professor Michael Schaub. So Michael is currently an assistant professor at RWTH, University. Before he obtained his PhD at Imperial College London and under the supervision of Professor Mauricio Barihana and Sofia Yaliraki. And then he started his postdocs at UC Louvain, University of Namur, for the MIT and Oxford. So a central methodological issue underlying his research is how one can study and integrate the multiple level of organizations, which are commonly found in a range of systems. So let's welcome Michael now. So feel free to start.
Well, thank you for the introduction. It's nice to be back in Oxford, if only virtually. So I've been at this seminar a couple of times myself in the audience, and now I'm sort of, well, in front of you, although not really, but you know how this is. Okay, so this talk is about signal processing on graphs and simplicial complexes, and I assume that most of you are very, very familiar with graphs. Maybe not so much with simplicial complexes, but that's not so much of a stretch. But maybe the signal processing doesn't come naturally to you as well. So I want to start with an ultra-fast introduction to signal processing, which is signal processing in 2 slides, essentially. Of course, this doesn't really duty to the topic, but you know, I'll do it nonetheless. And you'll see why as we go along, because yeah, the theme will be that this is really the essentials to extend this to graphs and to simplicial complexes. Okay, so here it is, a linear signal processing in 1 slide. So what's the mantra of signal processing, if I want to exaggerate and simplify at the same time a little bit? The mantra is basically that every data that we observe, we think of a linear combination as some signal and some noise. And of course, this is really like, what does it tell you? Nothing, because the key question is, of course, how do you model the signal and noise? So what do you think of? What is signal and what is noise? And historically, at least, we think of signals as maybe something coming from a physical process, so maybe described by an ordinary differential equation that doesn't vary too fast in time. So we think of a signal as something that's smooth, that has a low frequency, a low rate of change, if we talk about time signals, that is. And the noise, well, very often you just model it as uncorrelated white Gaussian noise. And of course, the stuff that really is hurting you there is then the rapid changes, the stuff that's really changing fast. And so that's the high frequencies here. So basically signal, that's everything that's smooth, and you know, noise, that's basically the rest. Okay, so then we want to actually process signals. We just don't want to talk about signals, we just want to process them as well. And so let's do this slightly more mathematical, if not much. So here, let's say we have data that comes in the form of this vector y here. And we think of it as a combination, a linear combination of the signal S and the noise vector eta. And think of eta as just a Gaussian vector, or a Gaussian random vector, right? And so now our assumption is that S lives in some linear subspace, and we want to, let's say, filter it out. And filtering just means linear filtering, that is, just means multiplying this signal y with some matrix. And the useful way to think of this operation is, of this filtering operation, is to think about it in 3 steps. The first is that we project our signal into a new signal basis, and we probably choose our signal basis such that we can express what we like to think of as signal in that basis, right? And now we can modulate certain frequencies. So basically, you know, you take it, the signal, you express it into these new coordinates, and then you remove certain coordinates, let's say, or change the coefficient of those coordinates. You modulate the frequencies. That's how you typically call this, and you transform back. So to give you a concrete example, again, in the sort of classical setting, would be to choose V, this matrix V of our signal basis, as Fourier functions. So every column of V would be a Fourier basis, a constant signal, you know, and then higher and higher order harmonics. And maybe what you want to modulate in terms of the frequencies. So this lambda is supposed to be a diagonal matrix, which coefficients that modulate each of these basis functions. For instance, you might want to filter out all the high frequency components, right? Okay, so this is linear signal processing in 2 slides, right? So now the question is, how on earth do we go from that to signal processing on graphs? Okay. And the key question is, in a way, again, what is signal and what is noise? So how do we define a smooth signal on a graph, and how do you define a noisy signal on a graph? And why do we need this? Well, because we want to do everything that we can do in signal processing, such as smoothing, interpolation, compression, what have you. We want to do that also on graphs. So with on graphs, I mean that we have signals or data that's associated to the nodes of a graph. So every node has an associated, in general, a vector, but let's just say it's a scalar, right? And we want to process that signal. For instance, we might want to smooth out some measured signal, let's say on this pretty manifold here, which is a human body, right? But in general, we want to do this on any kind of graph. And so how do we do it? Well, actually, we pretend that we were doing signal processing on graphs all the while. So in the classical setting of signal processing, you deal with signals defined on regular domains, such as audio signals, images, and videos. And we'll just pretend that actually what we did was graph signal processing for very specific graphs. So the time series becomes a graph signal processing application for a line graph, where basically every node now corresponds to one time step. And this goes on up until some finite but large time point, right? And the image is the same, right? So now we have an X and Y. We have sort of a grid, Cartesian product, 2 lines, if you wish. And now each point is basically a pixel, right? And it's connected to its neighboring pixels. And well, what is a video but a set of images concatenated? And so we think of the video as sort of like doing graph signal processing on this tensor-like structure, or this 3D lattice, right? Okay, so how does it help? Well, let's look at one particular concrete example here, and this is the discrete time setting, the simplest one. And so we have this graph here that goes from time 0 to time n-1. And for mathematical convenience, I'll just make the loop at n-1. I'll make the boundary conditions periodic, so I make this loop back. So it's a cyclic graph. Now, let's look at the graph Laplacian of this thing, which is just a diagonal degree matrix minus the adjacency matrix of this graph. And well, if you look at this for long enough, or if you have the right intuition, then you'll see that the Laplacian is actually a circulant matrix. Well, that means it's a matrix that describes a cyclic graph. So, and well, that has the implication that the spectral decomposition, or the eigenvalue decomposition of this Laplacian, gives you discrete Fourier modes. And what I mean with this is the eigenvectors of this Laplacian are in fact Fourier modes. And that's kind of cool, because then we can say, okay, we sort of have the connection to the classical signal processing ideas. But it turns out that you can have exactly the same observation for all the other regular grid-like domains that I've just shown you before. So the Fourier modes are the eigenmodes of the graph Laplacian. And now the idea is to say that basically what we did was signal processing based on the eigenvectors of the graph Laplacian all along. We just didn't know it, right? But that was actually what we're after. And so, yeah, that's how we move on now. So we'll now say, okay, smooth signals will be those that have a dominant contribution from slow eigenmodes of the graph Laplacian. Okay. And by the way, I see there are some questions in the chat, but I cannot see them because I don't have a mouse available anymore.
No, it's like someone doesn't have the audio right. So, but the audio in the room is correct. It's okay.
So, okay, I'll continue. So basically the idea is that now we've replaced Fourier modes as our set of elementary basis functions with the eigenvectors of the graph Laplacian. And we say that a signal is smooth if it has a dominant contribution from the slow eigenmodes of the graph Laplacian, meaning from those eigenvectors that have small eigenvalues. Okay. So here's an example to get you used to this idea. Let's say we want to do interpolation of graph signals, so smoothing. That is, we measure a vector y on a few nodes only. So here these nodes v3 and v6. And now we want to sort of interpolate in a smooth way these signals. So there are many ways in which you could do this, but a very simple one is to solve this following optimization problem. And it has two parts. And the first part is just a simple stay as close as possible to the measured signals, right? So minimize this two-norm of the difference. And then the second part is the interesting part because it regularizes the signal according to the graph Laplacian, right? And so if you can solve this analytically, and the solution is in fact a linear filtering operation. So it's a matrix times the signal y. And you can see it does kind of, you know, what you want. It smooths out the signal. So if you follow any edge of the graph, the variation of the signal is kind of smooth. So why is that happening? Well, it has to do with the eigenvectors of the graph Laplacian, of course. And to see this, we can just look at this quadratic penalty function here, because what does it do? Well, it really enforces smoothness on the graph. So if we write this out, we can see that this is essentially a measure of the variation of the signal on the graph. So it's a sum of squares. And what kind of squares? Well, you take for every edge, you take the difference of the signals on the two endpoints, right? You square it up and you sum it up. And the difference only matters if the two nodes are connected. If the two nodes are not connected, you don't care about it because the adjacency matrix Aij then will be 0 at that point, right? So the cost here is high if nodes are connected and their values are largely different, right? And of course, you can already see that there's also one signal, one assignment of xi's, right, with minimal cost, which is 0, and it's a constant signal, right? And arguably, you know, this is the smoothest thing you can get, a constant signal on the graph, right? So to get used to this idea even further, let me just draw here some of the eigenvectors of a toy graph Laplacian, right? And you can see below the eigenvalues that are associated to this, and it's sort of ordered in increasing smoothness, right? And so U7 is the constant eigenvector of the graph Laplacian, and it's very, very smooth, as you hopefully are convinced by now that, you know, this works. So, and now we can see that the higher the eigenvalue, the more variation we have along the edges of a graph, okay? Okay, so, you know, that is what the Laplacian can do for us. And now we might want to not just do this peculiar kind of smoothing operation with this linear filter that was the identity plus alpha times the Laplacian inverse and so on, but we might want to design general graph filters. And the way to do it is really, again, in this three-step process, right? So we design a graph filter H in this way. We choose the spectral decomposition of the graph Laplacian as our basis functions, right? And then we can put in any frequency response that we want. And this is what is sort of shown on this on the middle right. This is this function H of lambda k. So it means just like, you know, choose a function that transforms the eigenvalues of the graph Laplacian in a smart way, And this is one way to design a graph filter. And the other way is to, rather than doing this non-parametrically with this function h, you can say, okay, let's approximate this function by a polynomial, and then you go to this description that's on the left side. And so now you have here the coefficient hk that you can choose. And the idea is to choose the coefficients hk such that you can approximate any filtering function you want. And why is this interesting? Because the hk can also be learned, right? So you can think of in a machine learning setup, you want to learn a certain mapping from input to output. So then you tweak hk, you assign them to particular values so that this works nicely. And nowadays you don't deal with linear filters, of course, anymore. So the newest thing, the newest kid on the block is, of course, deep learning. So nonetheless, actually, a lot of this story continues to hold, because if you do deep learning on graphs, you get to something that's called a graph neural network here. And what is that? Well, it's just a concatenation of layers, where each layer comprises a linear filter. So this thing with the graph Laplacian in it and some coefficients of your choosing, and a pointwise nonlinearity. So you put a linear graph filter, pointwise nonlinearity, and you call it a layer, and then you stack up a lot of layers, and you make all the weights in there trainable, and you have a graph neural network. And why am I showing you this? Not because this is what I'm going to talk about later, but the idea is that everything that is about these eigenvectors of the graph Laplacian and these features will be also of interest in this context, because basically what goes in here is as your basic atoms, if you want to, if your basic dictionary as your basis functions are still the eigenvectors of the graph Laplacian. And so they are sort of the elementary features that you extract even in those contexts. And this is oftentimes useful to know. Okay, but now I don't want to talk about graph signal processing. I want to talk about signal processing on complexes, right? And now it's like, what on earth is that, right? So let's forget about the complexes because they're too complex for the moment. Let's just think about signal processing on the edges of a graph. So very often we don't measure signals on top of the nodes, but we measure things like flows of mass, of energy, of information, of goods, what have you, right? Money maybe as well. And the question is, can we still use this tool set of graph signal processing that I've just shown you? And intuitively you would think, well, yes, of course you can. And there's one catch, right? I mean, now the signals are on the edges and not on the nodes, so we have to do something about it. But clever people have thought about such things, and there's one idea that you could have is to use the so-called line graph transformation. This is sometimes also called a dual graph. So what's the line graph? So the line graph is saying I construct a new graph in which every edge of the old graph, of the original graph, becomes a node, and two edges or two nodes in this line graph are connected if in the original graph the edges were incident to the same node. So for instance, edge A and edge E, right? And they are incident to node 4, and therefore they are connected in the line graph, right? And now, if you do this transformation, right? So then you have suddenly now a line graph, and in the line graph, you have one node for every edge in the original graph, and you can think of these problems as, well, you just assign now the data to a node in the line graph, and you could do graph signal processing as before, or could you? Right? Or couldn't you? So let's look at the toy example here. And what I did here is just choose a very simple setup. We have a conservative flow, right? So this is like two perfectly cyclic flows. And I add a little bit of Gaussian noise. And now I want to recover the original signal from this noisy version, right? And I say, okay, I've learned in this talk, or maybe I knew from before, right? I can use graph signal processing to do this, and I'll do it on the line graph. And I run it, and what? Yeah, it turns out that the error is actually worse. So we actually made things worse by attempting to run like this moving filter here. And now the question is, why is that, right? I mean, what happens here? And it turns out that the problem is not the functional form of the filter here or something like that. The problem is really the operator, the Laplacian of the line graph. And because it encodes the wrong notion of a smooth signal. And let me elaborate on this a little, okay? So what we had here is basically a cyclic flow, right? It was conservative. It was basically everything that goes into a node comes out of it, right? But what kind of smoothness notions do we have encapsulated in the Laplacian of the line graph, or in the Laplacian, right? So there we said a signal is smooth if two nodes have signal values that are very close, right? And so in the line graph setting, that would mean that two edges that are connected have values that are very, very close, right? However, for this context, that doesn't make a lot of sense, right? Because let's say this flow in the middle, the 9, right, with value 9, it just splits up into 3 and 6. There's no reason why, suddenly a 9 should split up into 9 and 9. In fact, this is actually quite nonsensical if you want to consider conservative flows, right? So what you see that the line graph filter does, and it tries to enforce this notion of smoothness, it actually does a distributed averaging, right? Like all the values get very close. They get sort of around 5 here, right? But that's not what we want to do. What we need is instead an operator or a matrix that encodes the cyclic structure of the graph. It encodes properties of those flows, right? So we want to have an operator that does that. And yes, there is such an operator, and it's the Hodge-Laplacian. But let's focus on the simplest setup of it, which is a Hodge-Laplacian without any so-called faces. So if the graph Laplacian was B transpose, where B is the incidence matrix of the graph, then the edge Laplacian, let's keep it simple here, is just B transpose B. And what's nice about this is that the spectral properties exactly encode properties of the flow, in particular the null space, which is associated to 0 cost, right, is the cycle space of the graph. So it corresponds to all circular flows. And the image of that operator L1 is the gradient space. So that's all those kind of flows that you can create by assigning a potential to the node and just looking at the differences that is induced by those potentials. It's the gradient space, or sometimes also the cut space. And the edge-Laplacian is in some sense the little brother of the more general Hodge-Laplacian, which you can write here. And I'll get back to this slightly later, but let me continue this this story here for a second. So zooming out, what the general theme is that basically that almost 0 eigenmodes of the Laplacian will correspond to smooth signals. That's sort of what I'm claiming here. And we can do this for the Hodge-Laplacian. So the 0th Hodge-Laplacian is in fact the graph Laplacian. So these are smooth signals on the nodes. And you can go to the L1 Laplacian, which is the first Hodge-Laplacian, which will give you an indication for what are smooth signals on the edges, or what are flows. And you can actually continue and go higher. But here's another funny thing, or let's say it's an interesting thing about the Hodge-Laplacian, that if you ever did a class in vector calculus, then you've probably heard that any vector field can be decomposed into so-called gradient flows, curl flows, and then if you consider non-Euclidean spaces, then you can also add another type, which is the harmonic flows. And it turns out that the Hodge-Laplacian does exactly that for you, but in the discrete. So the eigenvectors of the one Hodge-Laplacian, they will basically span exactly the gradient flow, and they will span the cyclic flow, which is the harmonic and the curl. And if you don't have any faces in your complex, so if you're just talking about the edge Laplacian here, then the harmonic and the curl flow, they collapse, they just become one space, and that's the space of cyclic flows. Okay, so this was a bit technical, but let's fill this with a bit more intuition in life. So here is the same toy graph that I showed you before, but now I'm plotting you the eigenvectors of the edge Laplacian, right? So the eigenvectors are basically now functions that live on the edges. And you can see, again, the smallest eigenvalues are 2 zeros, and each zero corresponds exactly to one cycle. So this is great. This is nice. And what does the eigenvalue, when does it go higher? Well, it goes higher if your flow that you have on this graph has a larger and larger divergence. So if it deviates from flow conservation, in other words, if not everything that goes into a node comes out of it, right, then you have a non-zero divergence. And the larger that is, the less smooth that is, the higher the eigenvalue here. Okay, this is the intuition to have. And now, well, lo and behold, if you choose that Laplacian and you do the filtering, things get better, and we recover, or we get closer to the true signal, right? So great, right? So now we can do filtering in the edge space, and we can also do this in slightly different setups. So for instance, you might not measure the flows everywhere on your graph, but you might just measure it in certain places. Maybe, you just measure the traffic on a few streets in Oxford and you want to interpolate the rest. You can still do that with this technology. And well, what you need to do? Well, we now need to penalty for not having flow conservation, because that's sort of a running assumption here, is that the flows in the real world there, they have some kind of flow conservation. So we put the L1 Laplacian now in here as a quadratic term. We actually allow also for sources and sinks. If we know them, we can fill them in. And we arrive at a very similar problem to solve as before. So the first term is basically, again, saying stay as close as possible to what you observed. The second one is saying, okay, we penalize divergence and we account for sources. So divergence is allowed only at places with our sources or sinks. And the last term here is to make things, to make the solution unique, because we may actually have many, many cycles, and basically we choose a solution with small L2 norm. So if we do that, then we can run this setup here now on real traffic flows. And we see that this line graph filtering in contrast does much worse, whereas our flow based semi-supervised learning or interpolation based on the Hodge-Laplacian works out relatively well in comparison. Okay. So this is a computer science proceedings, right? And so basically our line is higher than the black line, so we win. That's the main point, right? So so the story so far, right? So I told you now that, okay, signal processing and graphs is basically, you just swap in the eigenvectors of the Laplacian instead of Fourier modes. And I've told you a little bit about this Hodge decomposition, which gives you this nice basis for the signals, and it gives you a notion of signals and noise, right? However, I haven't really talked about simplicial complexes yet, as advertised in the title. So let's get back to that, right? And what can we do actually more if we have that, right? So now signal processing on complexes with phases included, right? And so what are these mysterious phases? Well, a simplicial complex is basically an extension of a graph. A graph is something where I have zero simplices or nodes that are connected by one simplices or edges. And now simplicial complexes, you can have two simplices, which are basically, you can put in an area, right? An area that's bounded by edges. And you can put in a volume that would be a three simplex, right? And so how can you encode the structure of such a simplicial complex? Well, you can use, again, incidence matrices as you did for graphs. So you have two types of incidence matrices now. Well, I should say, I'm just going to concentrate on the L1 Hodge-Laplacian. That is to say, we're just going to consider simplicial complexes that have nodes, edges, and triadic faces, if you wish, right? And so now we can encode the structure of such a simplicial complex by two boundary matrices. So this is taken from the review paper by Federico Battiston et al. And the first one is the node to edge incidence matrix, right? And that we already know from the Hodge-Laplacian. And the second one is a triangle or is an edge to triadic face incidence matrix, right? And the way this works is to say, okay, for every of those elements, I define a reference orientation. So I have a reference orientation for bookkeeping of my edges, right? And I say, if my edge is aligned with my reference orientation of the face, then I put a +1. If it's anti-aligned, I put a -1, right? And then I can, build this this Hodge-Laplacian, right? So it's nothing but a matrix that couples edges to edges, okay? So this is how it looks like. And now what have I gained? Well, now in addition to having a cycle space, I can now distinguish two types of cycles, and those are the curls and the harmonics. And the curls are those cyclic flows that I can create by basically considering cyclic flows around filled triangles, filled triadic faces, right? And piecing those things together. So I allow linear combinations of any such triadic flows, and those I call curl, right? And the other ones that I cannot piece together as such, they're called harmonics, right? And okay, so this is the toy example again. Now, basically, I can distinguish this curl from the harmonic one, and the curl has a non-zero eigenvalue as well. And so what can I do more? Let's look at an example. So here, I'm just plotting a simplicial complex with some flows defined on it. Every triangle here is considered to be filled, so it's painted in, but those two holes that there are. And now for each of these holes, I will get 1 zero eigenvalue in my Hodge-Laplacian, and this will correspond to a harmonic cyclic flow. How do these things look like? Well, here's one representation. So this is a repeated eigenvalue. So the harmonic flows are in fact not unique, but you'll get always something similar to this, right? So the first harmonic flow is basically now giving you a counterclockwise rotational flow around the lower left hole in that space or obstacle. And the second harmonic flow is giving you a clockwise rotation around the upper right hole in that space. Okay, so now you have these two vectors. What can you do with it? Well, in the first instance, you could say, well, maybe I'll just, take every single edge flow that I measured and I project it onto these harmonic flows. How does that look like, right? Well, it looks like this. And now, I don't know, is that sort of interesting? Well, it kind of tells you how much aligned every flow you've measured is with each of these harmonic flows. But that's not so useful because actually, if you look at these projections, they're mostly zero. What's way more useful, though, is to now project trajectories onto those harmonic flows. So let's think about this for a second. So what is a trajectory but a sequence of edges, right? And so I can build an indicator vector for every trajectory by basically putting a +1 if I traverse the edge in the right orientation, the reference orientation, put a -1 if I go against the reference orientation, and a 0 otherwise, right? And now I can take these trajectory vectors and I just project them onto the harmonic components, and I get the pictures that are shown here below. So you can, for instance, now see that the trajectories, sort of the purple, pink, and brownish trajectories here, they occupy a very distinct space in comparison to the others in this embedding space, right? So, and they get there because they behave topologically differently with respect to these holes, right? If you sort of go back quickly, you'll see that they went straight through the middle. So they had a negative contribution onto the first harmonic flow, and they also had a negative contribution on the second harmonic flow, right? And the other trajectories, well, they behave slightly different with respect to the obstacles. So they land in very different places in your harmonic space. So what you get is a very low dimensional representation of this a priori very high dimensional trajectories. And this is a kind of a nice thing to have, because now with this vector space representation in mind, you can, do whatever task you want, apply any technology that you know of for dealing with data in a vector space. And the embedding basically encodes you this topological information. So let's do this with real data. So we're given here trajectories of ocean drifters. This is these are big buoys that drift in the ocean. I mean, basically a bit of plastic that swims in the ocean. And this is a very noisy, incomplete data. And now I want to say, okay, can we actually derive a very low dimensional representation of this? As you've probably noticed, right? This is Madagascar. I'm sure your geography is I mean, well, so this is Madagascar, and you have a lot of buoys that arrive from to Madagascar from the east, and then they either go north or they go south around Madagascar. And so, what do we do to deal with this data? Well, first we discretized our space into a hexagonal grid. You'll see this here. And then we said, okay, we'll basically connect. We treat every hexagon as a node. We connect two nodes if there have been sufficiently many trajectories that go between those nodes, between those hexagons. And the same with the faces. We basically say if there have been sufficiently many faces going through this sort of area, then we'll fill in the face. Of course, Madagascar cannot be filled because it's a landmass. So this will give you one big hole already. And then we do the usual thing as before. We encode our trajectories as edge sequences or as vectors, and we project it into the harmonic space. It turns out that the harmonic space here is again two-dimensional. And well, the left picture is easy to explain, right? So this corresponds to the harmonic flow that is Madagascar. So we now can basically distinguish trajectories that have a high projection onto this first harmonic flow and a low projection. And that means you either go north or you go south around Madagascar, roughly speaking. Now, the second picture corresponds to another harmonic flow. And this is sort of like a local vortex-like circulation that you have on the southwest of Madagascar. And, you know, this is kind of nice because actually in this case, we got this, even though in some sense by coincidence, but you can do this sort of in a data-driven way. You can say, look, if there's not enough flow going through this, you want to pick out these things. And this, in some sense, corresponds to an outlier, right? It's a very rare thing that you get this type of circulation there. And well, with that, let me conclude. So you can do actually much more with this. For instance, you can do outlier detection, which is something we're currently working on. But what I wanted to convey to you is that signal processing on graphs and complexes, you can think of really as a generalization of classical signal processing based on Fourier modes. The second thing that I wanted to convey is that the Hodge decomposition is a very nice tool to think about smooth signals in whatever domain you are in. It gives you a unitary basis for signals, and it gives you a notion of signal and noise. And I've shown you 3 examples about what you can do with this. So you can filter edge flows via sort of these cycle space ideas. You can do semi-supervised learning for flows of traffic, for instance, and you can do dimensionality reduction of trajectory data. And if you want to know more, you can go to my homepage. Of course, I'm happy to answer any questions that you may have. Thank you.
Thanks, Michael. So